Hey everybody, welcome back to another round of physics, and yeah, let's get going. Just to remind everybody where we stand, we are dealing with circuit elements, and in particular, we are going to talk about resistive networks. So we're going to be dealing with resistors and, for lack of a better term, I'll say networks. And how we're going to actually analyze these is using the relationship between a change in potential and the current running through a resistor. Now, one way to think about a resistance is that you can think of the resistance as being the constant of proportionality between a current and an applied potential, namely like this. Or if you prefer, a different way to write it, just organizing it differently, is that a change in potential across a resistor is given by the resistance and the current. I should also point out the unit of resistance is generally referred to, well, no, isn't generally, it is referred to as the ohm. Okay. And the symbol that we use for that is a capital Greek letter omega. Now we can see from the kind of the definition of resistance, we can see that an ohm, a unit of resistance, is equivalent to a volt per amp, or if you prefer more fundamental units, that is a joule second per coulomb squared. Now, truth be told, I can't think of a single time that anybody's ever quoted these units to me. Everybody just calls them ohms. So there's that. Okay. Because of that, I should say that this relationship, again, the fact that the resistance is the constant of proportionality between a current flowing through an element and the potential across the element, that is generally referred to as Ohm's law. Ohm's law. Okay. And this is the equivalent expression for resistors as what we've seen in capacitors. To remind you again, the capacitance of an object is defined as the amount of charge and the resulting change in potential. And so we could have kind of an Ohm's law for capacitors, which essentially tells us delta V is equal to Q over C. Yes, the reason I highlight this is that we will see one more Ohm's law like equation for a third circuit element. So to be continued. Now, going further with resistors, similar to capacitors, remember that capacitors store energy in the electric field, or analogously, it stores separated charges, and due to that charge separation, there is an electric field. Okay. Resistors, the purpose of a resistor in a circuit is to remove energy from the system or from the circuit. Now, if we want to think microscopically, what's really going on is that the electrons that are running through the circuit are continuously, without cessation, experiencing a change in potential, and so they're speeding up. What a resistor does is basically as the electron speeds up, it immediately removes that kinetic energy so that as the electron moves through the circuit, it moves at a constant speed. Or maybe a better way to say it is a constant kinetic energy. We should derive an expression to help us understand how quickly a resistor removes energy from the circuit. Okay. And to do this, we'll just start off with our relationship between a change in potential energy and the change in electric potential. So go ahead and remind yourself real fast. I'll go ahead and write this down here. I think we agreed in class we'll just use PE for potential energy. And yeah, we've got something like this, that the change in potential energy is given by the charge, whatever charge moves through this difference in potential. Well, now let's go ahead and play a little bit of math. We'll have fun with math. Basically, what I'm going to do is I'm going to divide both sides by a time interval. Okay? By a time interval, delta t. And now on this side, we have a change in energy, namely potential energy, per unit time. That is often, instead of saying a change in energy per time, we often say that that is power. Okay, that is the technical physicsy term of power, and we generally use a capital P for that. Okay. On the right-hand side, we have now this potential difference, that's staying constant. And so we're talking about some amount of charge that passes through the potential difference for a given amount of time. So basically I'm thinking, okay, we have this delta Q over delta T times our difference in potential. And here we recognize that a charge per unit time is a current. And so at the end of the day, we find that the power, the energy generated per unit time, is given by the current times the potential difference that the current is moving through. Now that expression, I'll box it in here, that expression is perfectly general. If you want to know, for example, the power of a battery or the amount of energy being produced per unit time, we simply take the current that is flowing into or out of the battery, take your pick. We multiply by the difference in potential, namely what's written on the side of the battery, and that will tell us how much energy per unit time is being generated by the battery. Similarly, okay, and I should say generated, I should say the amount of energy per unit time that's being supplied to the circuit. Similarly, a resistor, we could do the same thing here, and that will tell us the amount of energy per unit time that the resistor is pulling out of the circuit. Now, if we want to specify this in particular for resistors, we can now take this expression for power, we can take the expression for Ohm's law, and we can combine those two to get expressions dealing with specifically resistors. So immediately we see that if we just do a straight substitution of delta V, we see immediately that the power, the amount of energy withdrawn by the resistor, can be expressed as I squared times R. Of course, that's not the only thing that we could have. Instead, we could choose to rearrange this and get rid of, the I's instead. And if we do that, then we see that power could be expressed as V squared over R. So either of those expressions is perfectly fine. Well, now that we have that, now that we have this idea for a resistor, power is I squared R, or power is V squared over R. Okay. We should be able to use these ideas to come up with the rules for how resistors can be combined within a circuit. Okay. So let's go ahead and do that. And again, just to give you kind of the setup, let's pretend, for example, that I have two resistors in series. So I have one resistor, two resistors. Okay. And here's R1, here's R2. And the idea is that I would like to have an equivalent circuit, okay, and with a single resistor. Now remember, to have an equivalent circuit, what we need is that we need to make sure that something stays the same. Okay. In this case, we would like to ensure, right, that the potential drop from one side of the resistors to the other, the delta V has to stay the same. So from this location to that location. But you say, but Greg, that's automatically satisfied. That's the purpose of the battery. The battery ensures that the drop across the resistors is the same in either situation. So we don't have to worry about it. But the second thing that we have to do, right? The second thing is we have to make sure that the amount of energy withdrawn from the circuit stays the same. Or equivalently, that the current running through the circuit stays consistent. Right? Okay, good. So we have to make sure that the current stays the same. Well, that should give us some sort of idea. If I want to start off, I'll start off with I want to make sure that the power for either of these circuits stays the same. And now I will go ahead and let me substitute in this top expression, namely the total power that is removed from the circuit, the total amount of energy per unit time removed from the circuit. Well, that must be the current flowing through the first resistor times the first resistor value. And because these are in series, the current that passes through the first resistor must also pass through the second. And so I can use the same I, but now I'm dealing with resistor 2. Well, if I now think about the right-hand circuit with the equivalent resistance, I want to keep the current the same, and I would like to simply know what the equivalent resistor value needs to be. And now we have a goody-goody moment. We say, oh, wait a minute, goody-goody. Right? The currents cancel because I wanted those to be the same by design. And so we find out that when we have resistors in series, we simply add the resistances to find the equivalent resistor. So if I make that substitution following this relationship, I am guaranteed to have the same current running through either of those two circuits, and I am guaranteed that both circuits will remove the same amount of energy per unit time. And yes, that is perfectly generalizable. So if I say, wait, Greg, if I have 2 resistors, that's fine, but what happens if I have 3 or 10 or 50? Okay. So in series, it is the sum of the individual resistors is equal to the equivalent one. Okay. And you say, but wait, Greg, I've seen this before. You go, yes. And here we'll have to be careful. Wait until the end of the video, but we'll have to be very careful. Okay. Well, while we're at it, we might as well get the other expression. The second expression, you say, there is series, but what about if they're in parallel? Right? So we'll call R1 and R2. Good. Now here, again, we know what the drop has to be. The potential across each of the resistors must be the potential of the battery. And that by the nature that they're in parallel. And I would like to replace that with a single resistor of some unknown, we'll call it REQ, equivalent resistor. Well, let's go ahead. The behavior of the circuit, we want to make sure that the total energy removed per unit time stays the same. And we will go ahead and substitute on our expression. Now, I don't know the current flowing through R1. I don't know the current flowing through R2. I could find it, right? I could figure it out using Ohm's law and then instead use the expression for power that has current in it. I go, that's for the birds. Okay, I'll just use the expression containing the difference in potential. So, fielder's choice, I'm lazy. So what we have here is the potential drop across R1 plus the potential drop squared across R2. We want that to be equivalent to the potential drop across our equivalent resistor. And we have a goody-goody moment. And we find out, again, we can get rid of those, and we find out that if I add the inverse of the resistor values, I find the equivalent resistor. And again, yes, this is perfectly generalizable. So if I have multiple resistors, not 2, but maybe I have 50, Again, all I have to do is add the inverses. So sum in inverses. Again, drawing analogies with capacitors. For example, we found out that a parallel plate capacitor has a capacitance given by area times epsilon naught over d. Okay. So as the area of a capacitor increases, its capacitance goes up. As the distance between the plates increases, the capacitance goes down. So proportional to area, inversely proportional to the distance between the plates. Well, let's go for resistors now. And in some sense, yes, in a conceptual sense, you could say, well, resistors slow down electrons. What I should say is that resistors ensure that the kinetic energy of the electron stays constant. Okay, so maybe that might be a better way to say it. So it's not necessarily slowing down, but it's making sure that they move at a constant speed. Okay. So I like to think, you could say, well, how does a resistor do that? I tend to think about, for better or worse, I tend to think about highways. So let's think about a resistor as being kind of like a highway, and we'll think of the electrons as being cars. Okay. So first of all, let's say here, and I should have just had pictures, but we'll have to deal with Greg's silly pictures instead. Okay. Let's say you're trying to get home. I have no idea where home is. Drive safe. And you have two choices, right? You have choice one of driving on 2-lane road, or choice two is driving on 4-lane road. So the question is, okay, which road would you have an easier time navigating around traffic? Good. Survey says the 4-lane road, right? And the reason for it is because there is more opportunity. There are more lanes for you to maneuver between, and that allows you to flow through to get from point A to point B easier. You can flow around, you can navigate around a lot easier. Okay. Now, drawing the analogy with resistors, pretend that the road is the resistor and the car is, say, some electron. Okay. And the same idea applies. As the number of lanes in the resistor goes up, that gives the electrons more maneuverability to get around other electrons that are already in the wire. Now, how we would actually phrase that is what we would say is, as the cross-sectional area of the resistor goes up, the resistance goes down. Or a different way, the thicker the wire, if a wire is thicker, that means that there are more traffic lanes for the electron to maneuver. So I'm just trying to give you a conceptual idea that as the cross-sectional area goes up, the resistance goes down. Good? Okay. Put that on the back burner. Let's ask another question. So the second question, let's say you have a 2-lane road. Okay. And here's one, and then the second one. Okay. Good? Which one will take you a longer amount of time to complete? Yeah, you say, well, duh. Okay, if this is, say, a 1-mile road, and this one's a 100-mile road, okay, obviously the shorter road will take me less time to complete. And again, you could think of this, and now I say less time, but you could think of this as being another idea about flow. The longer the road, the longer it will take you to get to the end. Okay? And you could think of that long road makes it harder to get to the end. I mean, like in terms of traffic flow. Longer time means that it takes longer, harder to get to the end of the road. Okay? We could think of the analogy with resistors the same way. Okay? So the longer the resistor, as the length of the resistor goes up, the longer it takes to get to the end, and we perceive that as being a higher resistance. So as the length goes up, the resistance goes up as well. We can put those two ideas together. Okay, so now we've got that. Now, we can put those two ideas together. We know that the resistance, it must increase with length and decrease with area. And indeed, this is the case. Okay. Now, the last piece in there, and the same thing we could see with capacitors, it increases with area, it decreases with, for lack of a better term, I'll say length, but what we meant is the distance between the plates. And for a capacitor, if it's vacuum filled, we use epsilon naught representing the permittivity of free space. But if we happen to have a dielectric inserted, rather than epsilon naught, it's epsilon, where this is the permittivity of the material. It is a material property that encompasses how much it polarizes in the presence of an electric field. So the idea, though, is that it's a material property. We could have the same thing for resistors. Okay? We know that the resistance must go up with L. We know it must go down with area. And there must be something that incorporates the material out of which the resistor is made. Indeed, we call that, and now I apologize because we've seen this already, we've seen this variable used in a different context, and it means something completely different. Okay. Generally, historically, we again use the variable rho. Okay. And where we have seen it in the past in this course is that it represents the charge density, right? The volume charge density, how much charge per unit volume. Okay. Here it means something else. Okay, so be careful. We are currently in circuits. Rho has a different meaning in the context of resistors and circuits than in terms of in the context of the electric field and all that jazz. Okay, so unfortunately, don't kill the messenger. I'm sorry. In this context, this is referred to as the resistivity. Okay. So you have resistance. Okay. Resistivity is a material property, and it encompasses how easily charge flows through a particular material as compared to a different material. Okay. So, for example, the resistivity of metals tend to be low. I think I would have to look it up. This is a chart in your book, but I have to look it up. But I want to say the resistivity of metals is probably something like 10 to the, -6th. Pretty small. But if you look at the resistivity of insulators, stuff that we traditionally think of as non-conductive, I want to say that they're on the order of, I'll say 1. Okay? So they're 1,000,000 or 10 million times more the resistivity is 1,000,000 times larger or 10 million times larger. Now we could also see the units of resistivity. Okay? We know that the units of resistance are in ohms. On the right-hand side, we have a meter divided by a meter squared. And so evidently the resistivity must be in ohms times meters. You don't need to know that, but that's just for general, completeness. The nice thing about resistivity is that if I hand you some sort of material, say copper, you can use the bulk properties of copper. Namely, what I mean here is the macroscopic dimensions of a piece of copper to estimate its resistance. Now let's go ahead. We could start building out a chart. So we have capacitors, we have resistors. So first of all, for summary, you say units. Okay. Units of capacitance are farads. For resistors, it's ohms. Okay. If we're talking about kind of a parallel plate capacitor, okay, we know that it's area times the permittivity over the distance between the plates. Or if you want, you could think of length. But for resistors, you notice that there is an exact inverse relationship as capacitors. Capacitors go up with area and down with separation distance. Resistors go up with distance and down with area. And because of that, when capacitors are in parallel, the equivalent capacitor is given by the sum of the individual capacitors. In some sense, I think of it literally as, for example, if I have one capacitor and I have a second capacitor, well, let me just shorten these two wires. I'll make this wire shorter, I'll make that wire shorter, so that those two plates just end up coming in contact with one another, right? Like okay, let me do it in blue just so we can distinguish. I'll just make these lines really, really short so that those two capacitor plates are essentially touching. And how you could conceptualize that as I've made the area bigger. And because the area of the plates is now bigger, the capacitance should go up. Similarly, you could think of, for resistors, we showed that in the case of a resistor, the equivalent resistance, it actually goes down. Right? And we explain that by there's more lanes of traffic to maneuver. You could kind of see that just in parallel, right? I have a resistor 1, I have a resistor 2 really close by. So now you can see, okay, I've got one lane, I've got a second lane. And as I add more and more lanes, you would expect that there's more paths for the electrons to maneuver around. And so the overall resistance should decrease. Now, I didn't use it like that when we derived it. I did the derivation in terms of power, but the conceptual idea that there's more lanes and so the resistance should decrease overall, that's just the heuristic kind of conceptualization to be able to keep these equations straight. Now in series, yeah, we have the exact flip-flop relationship, right? For series, a capacitor, you could think of, I'll draw two capacitors here. And what we'll do is let's just shrink that center wire, that connecting wire, let's just shrink it down to 0. Okay, so let's just make that wire infinitesimally short. And what you could think of then is that one plate, the bottom plate of the top capacitor, perfectly aligns up with the top plate of the bottom capacitor. So I'll draw that in as red right here. Okay. And then I'll put the bottom plate in. There we go. But of course, what we do know is that the charge of the bottom plate of the top capacitor is exactly equal to the charge on the top plate of the bottom capacitor. And so the charge of these two plates, if they're perfectly on top of each other, it's like they're not there at all. There's no charge, right? They perfectly cancel out. And what you can think of then is that rather than having two plates of certain distance, you can conceptualize it as a single plate with a much larger distance. And we know that as the distance increases, the capacitance should go down. That means that helps guide us that the equivalent capacitor should be equal to the sum of the inverse of the capacitors. Well, how about for resistors? Resistors in series, we argued that the road is longer, and therefore the resistance should go up. And longer road, here's resistor 1, there's resistor 2, there's resistor 3. Okay. We'll just shrink down those interceding wires. So now we just have one long resistor. Good? Yeah, and you see now why we have to be careful is that the equation that tells us how to combine resistors in parallel looks the same as the equation that tells us how to combine capacitors in series. Similarly, the equation that tells us how to combine capacitors in parallel looks like the same equation on how to combine resistors in series. And you can see why that happens in the first place is because for capacitors, the area is in the numerator, whereas for resistors, the area is in the denominator, and vice versa. So frankly, I don't remember this. I don't memorize these. I am liable to screw it up just like you. Okay, I don't, right? Like, I do not encourage you to memorize these. What I encourage you to know is these heuristic arguments. Okay, if you know, okay, the road is longer, resistance should go up. Okay, which equation, which form makes sure that the resistance goes up? Ah, it's this one. Okay, so in series, that's the one I need. That's literally how I do it every time. If you're ever interested, yes, we'll see inductors, and we'll see another form of the equation. Same idea. I can't remember for sure. I think it's that inductors in series add, and inductors in parallel go 1 over. We'll derive it in another video, a week or two away from now. Okay. The other one, I always find it interesting as well. If you're thinking about springs, like physical springs, also follow this kind of relationship. If you put 2 springs in parallel, okay, and you want to replace it with a single spring of some new stiffness, which one, actually, I should ask you, which one do you think it'll follow? I have no idea what you said. I was just curious. It turns out that the stiffness of the spring is equal to... Oh, I put it in series. No. It's in parallel. Sorry. Yeah, it turns out the equivalent stiffness of a spring ends up being the sum of the individual stiffnesses. And indeed, if you put springs in series, the equivalent stiffness actually decreases. So you say, I'm never going to be an electrical engineer. I will never need to know this. Don't worry. There's an equivalent expression that mechanical engineers would have to worry about. And incidentally, yes, there is some sort of relationship that gives you the for lack of a better term, a way to calculate the stiffness of a material. Okay, and we see by analogy it follows kind of the capacitor stuff. And so it indeed will have something like the area, the length. Okay, and what ends up being here, this constant of proportionality, is referred to as Young's modulus. Again, it's a material property, and it has to do with the strength, the mechanical strength of a material, or more specifically of an atom. Okay. So I'll leave that for you for right now. Okay, but please bear in mind that, yeah, this comes in other facets, and you'll see this in mechanics of materials. Okay, that this idea will certainly be covered in that. Excuse me. This idea will certainly be covered in that class. Cool? Yeah, very good. Okay. Well, I think that's probably enough for right now. Of course, you could go ahead, you can do the same song and dance. You could build out a circuit, something like, I guess we could build out a circuit like this, and put a bunch of resistors in the circuit, and then ask yourself, oops, excuse me, we'll do it like this, and ask yourself, okay, can I take this circuit, R1, we'll call it R2, R3, and R4, and can I take that circuit and somehow come up with an expression to replace everything with a single circuit of value REQ? Now, I won't go through it. I mean, we'll do some problems in, lecture, that kind of thing. But this is the kind of problem that you can kind of ask yourself how to do and work through it using some of these rules for simplifying circuits. Now, that's not the only technique that you can use, but this is one of the first ones, particularly when you're faced with a quote-unquote simple circuit. Sometimes using this technique is helpful. It's the most time-efficient way of going at it. Okay? Cool. Okay, well, I think that's enough for this lecture. I thank you for your attention. Keep up the good work. I'll see you next time.